Hello folks. Okay, well, last time around we talked about top-down parsing in general. This time around I wanted to get a little deeper into some of the details. So the first thing we're going to take a look at is what's called recursive descent parsing. And so the idea is that we come up with a bunch of different parsing functions and use one of them for each of the different kinds of non-terminal language constructs we might encounter. And so each of these things is going to wind up calling others as it sees something that might be a function call, or might be an if statement, or might be a while loop. And so we'll take a look at a bit of the structure for this and see how we go. Then we'll go on and start looking at other ideas in terms of top-down parsing and look at a couple of algorithms. So the idea for our recursive descent is, again, for every non-terminal. So we'll have one for the top level non-terminal, whether it's start or program or whatever it is in our grammar. We'll have a different parsing function for each one of these things. So let's say I've got some non-terminal x. Right, so I'm going to have a parsing function for x. And essentially the idea is that this parsing function is going to go through and say, well, we've got all these different grammar rules that deal with x. And so I'm going to look around and try and pick the most appropriate one. And maybe if that doesn't work, I'll try a different one. And if that one doesn't work, I'll try a different one. But I'm trying to go through from most appropriate to least appropriate, given whatever the circumstances in the code happen to be at the moment. And for the grammar rule that I pick, it'll be something like x goes to, and then some mix of tokens and non-terminals. And so what I'm going to do then is say, okay, well, my input stream, whatever's coming up next in the input, if I've reached the point where I think I'm at an x, then whatever's next in the input stream should match whatever matches an x. So if I pick this as my rule, then I'm going to say, okay, well, the first thing I see should match a T1. So if T1 is a token, I can just look at the next thing in the input stream and say, oh, is that next thing the right token? And if it's not, then I can say, well, this rule doesn't apply. On the other hand, if that T1 is a non-terminal, then I need to figure out if whatever's next is appropriate for that non-terminal. Well, if I've got functions for every non-terminal, then I'm just going to say, okay, well, let's call the function for that one and see if it says it's okay. And so each of these non-terminal functions, each of these parsing functions for the non-terminals, is going to go through and chew up some of the input, that's some of the tokens that are next in the input sequence, and say, okay, oh, okay, I can tick off, yeah, I expected to see an A, a B, and a C, so, oh, yep, there's the A, there's the B, there's the C, yeah. And so it works its way through the next portion of the input stream, and then either returns a true, saying, yeah, it matched, or it fails. And if it fails, it returns a false, and we come back to X and say, oh, well, we'll roll back to wherever we were in the input stream and try again. Right? So you've got this kind of hierarchy of function calls going on where each one says, well, this looks like it should be a blah. Let's call the right function to see if it's a blah. And that's the idea of recursive descent. You've got this, again, if you're thinking of the parse tree for the particular source code program that we've got, the function calls correspond to those different branches of the parse tree. Right? I've got x. If I'm applying the derivation rule, I go from x to these things. I'm making that function call, and then for each of those, if they're non-terminals, there's going to be additional function calls branching out from each of those. So there's our idea, and I'm going to just take a quick look at a bit of an example for that. So this is pretty much running through the same sort of ideas I just discussed. So let's suppose that I've got a program in my source code that's this little blob here. I've got a function foo, and it's got an if statement in it, and then at the end we call foo. So just this little block here is our source code program. So that means that our grammar would have to have rules for things like, okay, well, a program is made up of, maybe a function. We'll keep it simple for now and say our program is made up of a function definition and then a statement. Right? And it would have to have a rule for a function definition is made up of, I don't know, whatever the tokens are, an open bracket, a closing bracket, whatever the statements are. and statements would be made up of a whatever. And so what will happen is our parser would have to have parsing functions for each of those non-terminals, right? It would have a parsing function for program, a parsing function for function def, a parsing function for statements. And again, that might have a couple of cases in it for dealing with the case where it was an if statement and a case where it was a function call, right? A parsing function for if statements. So we'd have this whole slew of them, and each of them would chew up whatever it manages to read through in the input stream and return true or false. Did it match or did it not? And so then, as the parsing program was running, it would start off by calling parse program, right, the top level one. And if that returns false, it means that the thing, it couldn't find a way to make the thing a valid program. But what's likely to happen is that, we call parse program, it goes through and says, okay, well, the first thing should be a function definition and the second thing should be a statement. So it calls the parsing function for a function definition and sees if that returns true. If that returns true, then okay, well, it found all the stuff that matched to a function definition, and whatever's left should be the statement. So then we call parse statement and see if it returns okay and says, okay, yeah, I chewed through the rest of it, and it was in fact a statement. Now, we would probably have an extra test at the end of the parse program here to make sure that we had actually consumed all of the input, all of the tokens in the input stream, but that is pretty much the basic idea. And again, each of those functions would be going off, and our parse function definition would be doing things like saying, okay, well, does it begin with the function keyword and then have an identifier and an open bracket and a variable, a parameter list and a close bracket and an open curly bracket and then a statement inside. And it would use, for that statement inside, well, actually, I guess probably for the parameter list, there might well be a separate function that you created to say, oh, well, let's have something that parses a parameter list. Right? And it just keeps going through saying, okay, well, check if this next input sequence matches the type of thing I'm expecting to see. And you call the appropriate parsing function for that type of item. And again, if one of these things fails on its first try using one of these rules, maybe the one that's parsing a statement in here tries to see if this thing is an if statement and succeeds. Maybe the one that's trying to parse a statement here tries the if statement first and goes, oh wait, that's not right, and goes back and tries the function call one next and succeeds there. Right? So they might be trying out a rule and saying, oh, that rule didn't work. Can I try out a different rule? Is there a different rule for whatever the kind of thing is I'm trying to parse? And eventually, either it figures out a correct way to parse it, or it fails and says, no, you've got there's something syntactically wrong in your program. But this is a pretty common way to hand code a solution to parsing out a particular input, a token sequence, right? To go through and say, okay, well, if I'm going to create my own little parser, this is a nice common sense way to do it, right? As a developer, you can see the kind of structure that you're trying to go through. If you've got your grammar, you can look at it and say, okay, well, if I'm working with a function definition, I'm expecting to see these things in sequence. And you do have to deal with the different possibilities, but you rely on having functions elsewhere to go through and parse out those pieces. So you're taking a sort of top-down design to checking the syntax and checking the structure of the program. All right. I will leave that part for the moment and plow on ahead here. So the way this is most efficient is if we don't wind up backtracking, is when we go to pick a rule, we actually pick the right one every time. So we mentioned in the top-down parsing section in general that there are grammars that are backtrack free, and in particular ones where we can look at the next token in our input sequence, and based on that token we can pick the correct grammar rule. So these are the ones that are absolutely ideal for this kind of programming, where if I can look at the next token in the input sequence and say, I know what rule to apply, then I just have to, in the case of our recursive descent, I just have to go through and call the right parsing functions for the things on the right-hand side of that rule. And either it will work or it will fail, and if it fails, I know that this thing is not valid syntax. So there's a category of grammars called LL1 that fit this criteria beautifully. So the LL1 actually stands for left to right scanning, so that means we're going through our tokens from left to right. Our grammar rules use leftmost derivations, so they always go through and apply a derivation to the leftmost non-terminal on the right-hand side, the leftmost non-terminal in the sequence that still needs to be derived. And we've got one character of look ahead, so you're allowed to look at the next character that's coming up in the input sequence. The next token that's coming up in the input sequence. So that's where the LL1 comes in. So in terms of figuring out if something is LL1 or not, just as a general rule of thumb, they can't be ambiguous and they can't have left recursion. So we looked at ways of getting rid of left recursion, whether it was direct or indirect. So if we're trying to work on an LL1 language, the first thing we'll do is go through and eliminate the left recursion, and hopefully we can manage to create an unambiguous grammar, although that's another issue. But we can come up with a more formal definition of when something satisfies, when a grammar satisfies LL1. So here's the idea. For every rule where some non-terminal can go to multiple different possibilities, so if A can go to X or A can go to Y, so if you've got multiple possible rules for A, then there has to be a way for you to pick which one of those is the correct version, the correct rule for A to apply under any circumstances. So there cannot be any token M such that both X and Y lead to a derivation that starts with M. So, there can't be an M where X creates some string that's M, blah, 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 where there is also a Y that creates an M something else. So you're trying to make sure that they can't both lead to a derivation that starts with the same character, the same token. So that's one of the things. And again, this is kind of obvious from our look ahead. If we've got to be able to pick the right rule based on the next token, then the rules better have distinct next tokens. Only one of them can lead to the empty string, or at most one of them can lead to the empty string. Right? Otherwise, we wouldn't know if A was supposed to go to nil, we wouldn't know which one to apply. So the other part of that is a little interesting. If one of them can go to the empty string, so if X can eventually go to nil, then we need to make sure that no Y rules can possibly lead to something that starts with a character that could come after A. So let's say it's possible for the first character after, whatever A turns into, let's say the first character after that could be a C. Well, we want to make sure that it's not possible for Y to lead to anything that begins with a C. Otherwise, we wouldn't know at this point whether we were supposed to use the rule, A goes to Y and Y goes to the C whatever, or we were supposed to go to the rule A goes to X, X goes to nil, and then whatever was coming after A generates the C. So this is the rationale for this second part. So we describe this in terms of follow A. So this is going to be a set of characters that can come after A ends. So the things that can immediately follow whatever A turns into. So we'll look at definitions of first A. So these are going to be the things that can be the first character in a string that A leads to, or the first token in a sequence that A leads to, and follow A. So the first things that can come after the end of A. So we'll look at some formal definitions for those. They are going to crop up a number of times as we're looking at our parsing and our grammars. So again, a little bit more formally, for any token, A, first A is just that token. For any non-terminal A, first A as the set of all tokens that can appear in the first character, or the first token, if you like, of any sequence that comes from A. And that includes nil if it's possible to derive an empty string from A. So again, they're just the set of things that can be the first token in the results of whatever A turns into. And again, for us, first of A is interesting because those are the things that we're going to look at in terms of our look ahead to try and pick which rule we can apply. Right? If we can look at the possible first characters in whatever A turns into, those are going to be the things that distinguish which one of our different A rules we apply next. So to compute first of A, if you've got A as some non-terminal, then you've got all these different rules of the form A can go to, y1, y2, y3, whatever they happen to be, whether they're tokens or non-terminals. Then for each of these different y's, if the stuff before it can all go to nil, then the first character in that y could be the first character in an A. So that's essentially what we're saying here. If everything prior to yi can derive the empty string, then whatever's in first of yi can also be in first of A. Right? So pretty much by definition, anything that's in first y1 is going to be in first of A, but the rest of them all depend on the stuff before them being able to go to nil. Follow A, so these are the sets of tokens that can come right after the end of whatever A turns into. So for any non-terminal A, follow A is again the set of things that can appear immediately to the right of A in a derivation. So if you've got a bunch of different things in your grammar where you can wind up with whatever A turns into and then an X, or whatever A turns into and then a C, or whatever A turns into and then an F, then X, C, and F are the follow set for A. And those are, again, interesting in that they allow us to identify where A must be over, or where the potential ending points for A. If you think about error checking in a compiler, if you've got a compiler and you want to be able to handle things like the user's got a syntax error in a function definition or something like that, but I would like to be able to keep processing afterwards and try and give them information on any possible syntax errors in the stuff after the end of that function definition. Well, if I can figure out what follows my function definition, I can figure out sort of what sets of characters probably mark the end of that function definition, and that's the point where I can pick up my compiling again to try and look for whatever's after that. So if I had 3 different function definitions, I could look for whatever's at the end of that first one and then pick up and say, okay, well, I can try and do some syntax checking on the second one and on the third one. Right? So this can have really interesting implications for us in terms of working on the error checking for our grammars. All right, but we've got to be able to compute this. So again, just in terms of definitions, what we'll do is say that for that start non-terminal, its follow set can include the empty string. And that makes sense, right? If you think about whatever your start non-terminal is, it can turn into a bunch of stuff, but then there's going to be nothing after that. So we make the follow set for our start non-terminal just simply that empty string. Then for everything else, if we've got a rule like some non-terminal W can goes to whatever X is, whatever A is, and whatever Y is, where A is a non-terminal here, X and Y might not be, then everything in the first of Y is in the follow set for A, right? Anything that can be at the beginning of Y can be immediately after A, right? That makes sense. But we won't include the empty string in that. We're going to rely on our next rule for generating the correct places where an empty string can come in. So for the next one, if we've got W can go to XA, then we'll figure that, okay, well, the empty string can be there. Or if it can go to XAY, where Y is in the follow set for, or pardon me, where the empty string is in the follow set for W, will allow it there. So this is going to create a sort of transitive relationship where if W has got the empty string in its follow set, and we've got blah blah blah, Y can go to nothing, then the empty string could come after A, right? W can have nothing after it, Y can go to nothing, so A could conceivably have nothing after it. Blah. So we get this transitive relationship that will correctly expand the empty string to exactly the non-terminals that it could follow. All right. So first and follow are going to come back and haunt us again a little later in our work. But I want to go on and look at a couple more of these ideas for going through and having an iterative solution instead of the recursive one. So these are still going to be top-down, right? We're still working from our root non-terminal, but we're going to try and look for an iterative process instead of a recursive one. So what we'll do in this case is use a stack to keep track of things that we're trying to process, and this stack is going to allow us to eliminate the recursive idea. So we're going to keep track of the current item that we're processing, and that will start off with that top-level root non-terminal. We'll have a stack that keeps track of the things that we still need to process. So if I apply a rule and it says that, S goes to A, B, C, then I have to match A, B, and C against the tokens that are in my input stream. So I'm going to put these A, B, and C onto the stack. Actually, I'm going to put them in reverse order on the stack, the Y at the bottom, or pardon me, the C at the bottom, the B in the middle, and the A at the top. And say, okay, I've got to process these things. I'm going to have to pull A off the stack eventually and see if it matches the tokens at the start of my input stream. And then once I'm done with that, I'll pull B off the stack and see if it matches the input tokens that are next. And then I'll pull the C off the stack and see if it matches the tokens that are left at the end. So we're gradually going to be pushing things onto this stack as we realize we have to deal with them, and then popping them off and matching them up against tokens that are in the input stream. So that's the sequence that we're going to go. So while the stack's not empty, and there's still stuff left to read on the input, right? Ideally we want to go through this, and if our source program is accurate, is valid, then we should wind up processing everything in the stack at the same time as we've run out of everything in our input stream. So we're going to repeat until we're finished. Again, keep going as long as there's still stuff in the stack or still stuff left to read in input. And we'll take a look at whatever item we're dealing with right now. If the item we're looking at right now, so something that we've pulled off the stack, is a token, then it better match whatever's front in line in the input stream right now. So if the two of them match, then I can say, okay, I have ticked one more thing off. I can discard this current token, and I can discard that input token and move on to whatever's next. So I'll grab the top thing off of the stack at that point and read the next character, the next input token, and proceed from there. So if the top thing's a token, I'll just see if it matches. If not, we've got a problem. It's an error. If it does match, then we can discard it and move on. The other case is if the thing on top of, or if my current item is a non-terminal, right? So in the beginning it was our start non-terminal, for instance. In that case, I'm going to look at that next character in the input sequence, and I'm going to look at the rules that are available for that non-terminal. And again, since I've got this look-ahead idea, I can say, well, I should be able to match that non-terminal with that look-ahead character and pick the right rule. So when I do that, I'm going to push all of the stuff from the right-hand side of that rule onto the stack in reverse order, and then grab the top one off the stack and use that as my new current. So this will be the idea that I try and walk through. So I'm just going to, again, quickly pop through some of this. Let's see what I did with this. How about... yeah, that looks about right. So what we'll do here, let me see if we can make this a a little more readable. So I'm going to say that here's the grammar that I'm playing with over on the left-hand side here. So I've got my start non-terminal s can go to either x or y, or to the two non-terminals x and y, where x can be an a followed by an x. So there I can wind up with a bunch of a's in front, or x can go to a c. So I can wind up with a whole bunch of with 0 or more a's and then a c, and then we'll have the y side of that afterwards. So the y's can go to a pair of d's on the outside with a y in the middle. So every time I add a d at the beginning, I'm adding a d at the end. Or it can go to an e, so there's going to be an e at the middle here. So the y half is going to look like a bunch of d's, an e, and a bunch of d's, but the number of d's on each side of the e are going to be the same. So a star c, d to the n, e, d to the n is the language that we're accepting here. So let's say we've got as the string that we want to go through and parse at the beginning, say this is my input. I've got A, C, D, E, D, and I want to see if that's valid under my language. So I'm going to see if I can come up with a derivation using this kind of iterative approach. So I'm going to start off with my current symbol is my start non-terminal, so it's the S. And at the moment, my stack's going to be empty. So I try and pick a rule for S. So I look at that. Well, there is only one rule for S, so I guess that's pretty straightforward. So I pick the rule S goes to X, Y. And I take the stuff on the right-hand side and push it on the stack. So I push the stuff that's on the extreme right first, and then move from right to left, pushing things. So I push the Y, then I push the X. So once I've got the stuff on the stack, I'll pop the top element off and use that as my next current. So I push Y, push X, then pop X into current. And of course, if you're looking ahead at this, it would make sense to quit this one early and instead of pushing X and then popping it into current, if I just took that last one and assigned it straight to current. But we'll keep it like this for now. So now I've got X is my current, and I've still got A, C, D, E, D in my, my sequence of input tokens. And now I've got Y sitting on the stack. So my algorithm says, for this, I need to pick a rule for X. Well, I look at that first character in the input, it's the A, so I'm going to pick my rule X goes to AX. And so for that, I'm going to push the X onto the stack, push the A onto the stack, and then I need something to replace my current, so I pop the top thing off the stack. So now my current is A, and again, I've still got this same input sequence, and now I've got an X on top of the stack and a Y underneath it. So I look at that and say, well, A and A match. Yay! So I can discard them and grab the top thing off the stack as my next thing to process. So now I've got X to process, and I've got C, D, E, D in my input sequence, and I've got Y sitting on the stack. So I need to pick a rule for X. Again, I can look at that next character of input, so I'm going to pick my X goes to C rule. I'm going to push the C, and then I need a new value for X, so I'm going to pop the C into current. And now again, I proceed and, hey, wonderful. I've got C as my current token, and I've got C at the front of the input. They match, so I can discard them and pop the top thing off the stack as my new current. So now I've got Y in the current, my stack's empty, and I've got D, E, and D in there. So I want to see if the D, E, D matches a Y. So I've got to pick a rule for Y. Well, I can look ahead at the first character, so I'm going to pick the rule for D. So I push the D, I push the Y, I push the D, and I need a new value for current, so I pop the top D into my current. So now again, I've got D as my token and D, E, D in front. Those two D's match, so I can discard them and pop the top thing off the stack as current. So now I've got my Y, I've got ED in the input sequence, and I've got that D still sitting on the stack. So I have to pick a rule for Y. Well, I can look ahead, see there's an E coming up, so I pick the Y goes to E rule. I push my E, and I need a new value for current, so I pop E into current. And the two E's match, so I discard those and pop the top thing off the stack. So now I've got D, and I'm left with D in the input, and those match, so I'm done there. And at that point, once I discard those two, my input sequence is empty, exhausted, and my stack is empty, so I'm actually done. I've met the requirements, and this string is valid. And I've got a derivation sequence that tells me which rules I should have applied to which non-terminals as I go through this. So in effect, if I record these or print these, or if I wanted to, I could build my parse tree as I went through these steps. Each time I recognize a rule, I could build my new piece of the parse tree, and I've actually got a decent parsing of that string under that grammar. All right. So we've got this iterative process that, again, works reasonably well as long as the grammar is suitable. If our grammar wasn't backtrack free, then our algorithm here would have to include the possibility of backtracking and picking a different rule. So rolling back what we'd taken out of the input, going back to whatever we had at the on the stack before we applied that rule and picking up from there. All right, I wanted to take a bit of a look at the possibility of either using direct coded or table driven approaches to this algorithm. So if you recall with our scanning, we said that we could either take a table driven approach where we had a kind of generic algorithm and we just looked up in the table what, in that case, which transition to apply. We could do something here where we had a table that told us which rule to pick next. So we could take that kind of approach, or we could take, again, a coded approach where we actually had the decisions hard-coded into our parsing program. So either of those would be a valid approach. And again, they have much the same trade-offs. The size and speed of the table for lookups versus the size and speed of the hard-coded executable, the hard-coded parser. So again, similar issues, and you can take similar approaches to implementing them. Now, for a compiler, a big part of what we're interested in doing is providing the programmer with decent syntax messages, decent warnings, decent error messages if their code contains errors. So we really do want to make sure that we can, where possible, recognize a problem and continue parsing in spite of it. And this is where the look-ahead characters and those follow characters help us out so much. Right? The look-ahead character lets us know what kind of structure we should be parsing now. Right? It lets us decide the correct rule to apply. So within the context of that rule, we know what we should be seeing, and we can think about what kinds of error possibilities and what kinds of error messages we should be providing the programmer with. If something goes wrong, we can use that follow set to kind of go through the whatever's coming up in the input sequence and look at where we can try and recover from that error and pick up processing with whatever was after the broken structure. All right. What we will do next time around is to take a look at just a simple C program that follows this kind of LL1 parser kind of idea. So we'll take a look at just a sample program there and see how we can proceed.